Okay. Can you guys hear me?
Yep.
Okay. I can't get my camera to work. I don't know. Can you see my document camera?
Yeah, I can see it.
Alrighty. We got a few minutes before we get started. Are there any questions? Yeah, there are new office hours this week, and it will be Thursday morning as usual, plus Friday at 2 p.m. Any other questions or comments?
Professor, did you announce when the office hours have been changed to?
Yeah, it's in the chat. It's so Thursday morning as usual, and Thursday morning we have it at 9 o'clock, and then Friday at 2 p.m.
Gotcha. So Thursday is the same, and then Fridays in the afternoon.
Yes. Okay. Are there any other questions or comments before we get started? Okay, if not, then let's get started. So tonight, we're going to go into exam prep mode. We have some. We have there are a few loose ends regarding the Uranus derivative. And other than that, it's recap, questions, and if anybody volunteers, we can also do dry runs. Maybe we can do this next time. If anybody wants to try it out, next Thursday could be a time. And I should also say I got there were some early evaluations. We can talk about those. Right. So next week is the next week are the all exams. Again, if you haven't signed up, please send me an email about a time slot that you would like. You can see the current schedule on Canvas. Okay, maybe we can start with the latter point here. Let me just share how these evaluations look like on my end. So here, this is how it looks like when you get them on my end. So we are 23 students. 15 of you have responded. We are tonight, I forget how many people had logged on. Let's just do a count. We have 13, so that'll be 12 students and myself logged on. Okay, so here's the sheet that you guys fill out, so you can see is it organized. There's one student who is not happy, and then 13 out of the 14, they're not too unhappy. The same picture down here, to student comments and questions, people seem to be moderately happy about this. There are, one thing that stands out is this question here about online. People are not happy about the online format. So I don't really know what to do with the latter part here because I don't have any say in this. I can tell you my opinion is if I were to fill it out, I would have put my name in the top one too. I don't think this is the way that one should master math. I will say I understand why we're doing it. It's just unfortunate. Going forward, I am not sure what the format is going to be. I would imagine that Rutgers is going to follow many other higher institutions that will offer a hybrid in the future. So classes will be offered in both in person and in pure online versions. Exactly how that's going to unfold, I don't know. I can tell you that in the math department there are lots of meetings. There's another meeting tomorrow about this Proctor track. Some of you probably have dealt with Proctor track at some point, and there's been a lot of frustration with this, both from the students, but also from the professors and the instructors. So there's another meeting tomorrow about what to do with Proctor track. It seems like it's not doing so well. Some of the comments I want to discuss a little bit with. So, what did you like? Well, it seems like the material is interesting. What would you like to have improved? Okay, so with these comments here, there are some things that we can address, and there are some of the things that we cannot address. So one of them is try to slow down the pace. And even one student is saying that you should really split the course into 2 courses. And so I can only agree. I would very much like to see this course being split into 2 courses. It is easier said than done to get people higher up that make these decisions to actually do it. I have been at Rutgers since 2017, and I agree. It would be nice to get this split into 2 courses. There is a discussion about it's hard to keep up and the material is difficult, and I agree. This is a challenging course. The pace is one thing. It's also the material is not trivial. There is a comment about if we can lower the level. And this is just difficult because the material that you're seeing, this is the that is the basic math finance material. I don't know how to lower the level. There's a student here who's saying that it feels like this is being taught at a graduate level. I don't want to be a graduate student and I don't want to learn at that level. So when you talk about grad level, there are 2 levels, right? So there's a PhD level and then there's the master course level. This here is not a PhD level course. This here is the level that you guys have been taught at. This is the same level as being taught for the master students. These 2 textbooks that we're using, these are textbooks that were written for master students. There's a comment down here about the textbook that it is too much for 1 course. Yeah, we're not going to cover all the material in the 2 textbooks. And the reason that we're using these particular 2 textbooks is because those are the best. This is the best material that you can find on this topic. So you can find lots and lots of other books on this topic, but you cannot find anything that comes close to Steve Sharif's 2 books on it. And this is the gold standard. It's being used throughout the US and throughout the world on this topic. So you see, given that this is the gold standard, and we are covering material coming from these 2 books, there is really no way around it. We can't lower it. If we are to lower it, we're going to create a course that has a lower quality. And we can't do that. There's a question about if we can have a review session. Yeah, so this is the plan, right? This is what we're going to be doing tonight and also what we're going to be doing on Thursday. Work through more examples and slow it down. We can do that, but the consequence is that we will not get through material that the course description that you find online is discussing. There are questions here about students' prior knowledge. I mean, so we're not assuming. I'm not assuming that students know about sigma algebras, and I'm not assuming that students know about suprema and infima. These objects have been defined in this class. We're not spending a lot of time on a concept like a supremum, simply because we don't have time for it. Sigma algebras we spent quite some time talking about. Okay, so in terms of slowing it down, we can try. We can try to build in more examples. We can try, at least tonight and as well on Thursday, this is going to be largely covering material that we have already discussed. Okay. Are there any questions or comments on these relations? Are there any questions or comments on these relations? Typically, what happens in relations is we get students that are either very happy or very unhappy. Here it's a little bit different because there was actually a large number of you guys that filled it out. So this is awesome because it's going to give a more precise reading of what the students care about. Are there any other questions or comments about these evaluations? Okay, if not, then let's start talking about. So as I said here, if anybody wants to do a dry run next time, I am happy to do a mock exam. Exams if there are more than one.
Professor, when we do this oral interview, is it like are you gonna like show us a question and then like ask us to walk through it, or like do we show the question and then write on it? How does it?
So what happens? So I did 6 exams this morning, so I can tell you how that went. Okay, so for the oral exam, right? So this is 20 minutes. Okay, so you need your ID, and then you have your choice of media. And the students that I saw this morning, they chose, this is either going to be whiteboard on Zoom or cell phone. So you have to make a choice. Like, what do you want to do? Do you want to use Zoom's whiteboard, or do you want to use your cell phone as a document camera? I posted a link on Canvas that will take you to YouTube. That'll show you a video on how to transform your cell phone into a document camera, which is what I'm using. I don't use my cell phone. I have a document camera, but you can set it up such that your cell phone, if you have a cell phone, it works as a document camera, and then you can write on a piece of paper. I should say that you need to make this choice here before the exam, right? This is something that takes time to set up. So you need to make a decision on how you want to do this. You cannot just set it up when your exam starts. This is way too late. Set it up and then come to either office hours and see that this stuff works. So that's the first thing that has to happen. And the second thing is, I'll pick a problem. On the sheets of, I think there are 19 problems.
Oh, from the midterm review sheet that you like post in the beginning
Yeah.
this semester.
And so I'll pick one of them, more or less randomly. And then I want to see you try to solve this.
But
I don't want you guys to take the solution and put it up and then just go through it step by step by step. There are students that will try to do this. It does not end well. You will not get through an oral exam by memorization. This is just a recipe for disaster. You need to understand this stuff. And so what happens is that when you start writing the solution out, not just you, anybody, when anybody starts writing that solution out, at some point there's going to be a mistake. Like there's going to be a typo, there's going to be some small mistake, and you start poking around in it and to figure out if the student understands this or does not understand it. And then based upon that outcome, the exam is there's going to be more questions coming. So this is the starting point. Right, so it goes without saying that it's probably a good idea to look at these 19 problems before your exam. Because if I pick problem number 8 and the student has no idea about what problem number 8 is about, this is not off to a good start. So that's how it's going to go, and then there'll be lots of follow-up questions. Right, so it depends on if you can go through this problem that I more or less randomly picked. If that goes well, I'll ask you something that is harder. If it doesn't go so well, I will start poking around to figure out where your knowledge level is. And for some students, this goes very fast. There was one student today, after 10 minutes, he plowed through everything. So then we were done with this. There were some students that struggled quite a bit. So I will tell everybody the same, as I told some of these students that were struggling earlier today. The way to attack these situations is to really ask questions before the exam. So you're not going to get, this will be the first time that you ever speak about the material will be during your exam. You have to practice, right? And some of you using my office hours, I think last time I had office hours, I had 8 students, which is out of what we were 23. So 8 students out of 23, this is about a third, and this is quite high. And so those students that are in these office hours, and you will then participate and you'll ask lots of questions and you'll make mistakes, and it typically goes better when there's been a lot of interaction before the exam, and then the exam comes and it'll be easier. That being said, there are some students that can do this for the first time too. And then what's going to happen is that when we're done with all of this, I will give you some feedback about what went right and what went wrong. And then when I'm done with all the exams in the batch, I will send individual emails where I'll assign a grade for your performance. Okay. Are there any questions about the structure?
I have a question.
Yes.
So if you're just going to pick like a random problem from the sheet of 19 for each student, would you say the relative difficulty of each problem is about the same then?
Yeah, so I understand there is a concern about some students being favored over others. My wife asked me, how do you actually do this rubric? Because we are very used to having that this question counts this many points and this question counts that many points, and then we add them up, we get a tally, and then you sit in that bracket. That's not how it goes with all exams. It appears on the student's end as a lot more subjective. So the way that these questions work is we'll start out with one of these questions on the exam sheet, and then depending on how that goes, if it goes well, I need to make sure that the student is strong enough to get a higher grade, right? So I'll start asking more difficult questions to bring the student up to an A. If it doesn't go well, these questions that are on the sheet, they are aimed just as a starting point, right? And so if it doesn't go well, I will start asking simpler questions. And if they continue to not go well, then the questions become at the threshold whether or not the student is going to get a C or below. So it's going to float. So even though the questions, when you read them, they might appear as very different in level, very quickly, it doesn't really matter. It's not going to be like those 20 minutes you're going to be spending the majority of those 20 minutes trying to solve one of these problems. It's just a starting point.
Okay, thank you.
Yeah, so I can see that if this is new to how we do all exams, it might be a little bit like, am I going to get treated fairly? So just keep one thing in mind. Your all exams, they're all recorded. And I'm going to store that on my computer. It's not going to get put out into the, it's not going to be put up anywhere on the website. But what it means is that there is a very specific track record of your performance. So if you're not happy with the way that I grade your exam, this document can now be used for people higher up in the food chain if you want to pursue a complaint on how your all exam was graded. So there is this aspect, right? That there's a very specific document. Like it's not like there's going to be, if you feel like you're treated unfairly and I'm not willing to listen to your subsequent points of view, well, let me take this document, we'll hand it off to people higher up in the math department's food chain and ultimately in the dean's office. It is not, it might appear like this is a quite random process. I can tell you from the professor's point of view, it is doing all exams it's a much more precise measurement of the student's ability than it is to do written exams. The same thing, some of you have already told me that you're quite nervous and you're quite uncomfortable with the format, and I understand that. I can also tell you that it's completely normal, and I can also tell you that this is not unusual. The beginning is always rough. I don't care if you make mistakes. The problems that I care about is if there is a fundamental issue. For example, if you don't know how to relate expectations of a random variable with integrals with respect to a density function. If you don't have such a structure, if that is not clear to you, then it's a problem. And my point is that even though you're very nervous, you will still be able to convey this. I should also say that all exams, this is something that you don't see it at the undergraduate level very much in the US. But as you move higher up, if you go to a PhD level course, professors use all exams there because they give a much better read on the student's performance. You don't use them at the undergraduate level because it's believed to take up way too much time of the professor. And so people don't use it so much. So here, I'm dedicating a week of my time to do your all exams, and the same thing for the final. So everybody gets a fair shot at it.
So, what kind of follow-up questions might be asked?
But it depends on if you do well or if you don't do well. And this is dynamic, right? If I see you make a mistake, okay, so what could a mistake be? So as an example, so something like this comes up quite a bit. Like, it cannot be a surprise that in this class, you're going to be computing conditional expectations. Okay, so say that, say you want a prize. Say you want a prize, I think there's an example with like Sn squared. This is the payoff. So you want to price this. This is what you get at time in at the end, right? Okay, so that could be something like is the conditional expectation of Sn squared given Fn, is this a martingale? That could be a question. Okay, so in here there'll be, you need to know what a martingale is. So let's call this thing here for Mn. So for those of you that do not understand, if you can't follow what I'm saying at this point, you have to interrupt me, right? I cannot read your mind. So this could be a question that would come on. You want to price this object? Okay, so you have to start computing conditional expectations of this kind of payoff. So let's just keep the interest rate here to be 0, so we don't have to put tildes everywhere. So to solve this, to answer this question, is this a martingale? You need to know what a martingale is. So you see, Richard, if you don't know what a martingale is, then we're not going to ask a more difficult question. So the answer here is, so if you don't know, well, then you're going to get, then there'll be something that is easier.
Okay, I think I understand it. It's like much more obvious from your perspective whether someone knows or doesn't know. Something because you're teaching cars.
You have to understand that math finance, this is what I've been doing since I was 18 years old. I'm in my mid-40s now, right? So I've done this for 25 years. I was moved from Europe to the US to do research in this field. I've been doing this all my life. I've seen, there was a discussion about it. I think I've had about 1,500 students in courses like this. So there's a lot for me to learn, but I have seen this for so many years. I do believe that I can recognize if you know what a martingale is and if you don't know it. So I can tell you today that there were some students that didn't know what a martingale was. And there were some students that did know what a martingale was. So if you don't know it, I'm going to ask an easier question. So for example, I could ask them, instead of computing this conditional expectation, can you compute just the unconditional one? Can you write out what this is? If you can't do that, maybe can you write out what this is? If you can't do that, can you write out what the expectation of a Bernoulli is? If you can't do this, can you do it without the tilde? If we are down here and you can't answer this question, this is where the bottom is. If you can't answer this question, it is not good. There's not much I can do to save you. This is down where we are either at a C or we are below in a failing range. If you are to fail, the exam is going to be a bit longer because I need to make sure that this is not the only hole. Now, if you answer yes, you actually know what this is. You know what a martingale is, then I want to see the proof. Can you prove that this is a martingale? Can you compute? Can you provide like these? Can you provide these iterative functions that takes you from the conditional expectation from Sn squared to Fn minus 1? Can you write out what this function here is? I think we call these for Fn minus 1 of Sn minus 1. Can you find this system of functions? If so, what do the functions look like? Say that you do this. So now we're talking about the difference between, is this a B or is this an A student we're talking about? This here, this is something you had in class. This is something that has been in the homework. So if you really want to go up and get an A, I would like to see a little bit more here. So then I would ask you, for example, here we have an expectation under P tilde. I would say, can you write this as an expectation without the tilde of something like this? Can you figure out how to go from these P tilde expectations to the P expectations? Can you link them? There's a question from Alice. Alice, I made my life easier. I put R to be 0 up here. Alice is asking if I'm missing an R. Yeah, so I just made my life a little bit easier. So then my question is, can you figure out what to put here? Okay, now it becomes harder because what is the connection between expectations on the P and the expectations on the P tilde? Now you need to know something about Radon-Nikodym derivatives. So now it becomes something like, do you know that you should put Cn here and that you should write Sn squared and you should divide here by Cn minus 1? If you knew that, now you're in the A range. Then can you also tell me something about Cn? What does that look like? So you see, because all exams have the dynamic component, we can go down in these trees here. And there's a big difference between being able to compute the expectation of a coin flip and then talking about Radon-Nikodym derivative processes. And most students, they fall somewhere in between here. When I start pushing them around over here, most of them get a little bit like, I don't like this so much. And this is okay. We just have to figure out where the students fit in this. You're not going to get punished. You know, some students, you forget to write tildes here. This is not a big deal. Try to do it correctly. Alice pointed out that I should have put an R in here. If you do this stuff and you forget to put the R, it's not a big deal. Like putting a constant, not putting a constant, this is really not going to be the end of the world. What is going to be the end of the world is if you cannot relate expectations, for example, to if I give you a normal and I'm asking you if this is standard normal, I want to know what the mean and the variance are. So if you don't know that the mean of a standard normal is that 0, and if you don't know that the variance of that standard normal is the 1, this is not good. Okay?
Okay.
More questions?
Yes.
Yeah,
Sorry. So how would one prepare for the harder questions? For example, the Radon-Nicodemus derivatives. How would one prepare for insight that you will ask from that?
I mean, so this is something that that we either have touched upon in class. This is something that is in the textbook somewhere. This is something that is in a problem that's been posted somewhere. There are questions on the sample sheets that use the Radon-Nicodemus derivative. This particular set of problems that you're seeing here, one place you can find information about this is we go to Canvas. This is your Canvas, so you go down to modules. I put up some extra problems somewhere. Extra problems right there. So there were some questions about base, and if you flip further down, there are actually a bunch of questions on Radon-Nicodemus. These Radon-Nicodemus processes. These are going to come somewhere in the end. So that's C. So there are problems out there. This is an expression for how the Radon-Nicodemus derivative looks like. Compute conditional expectations of it. It is out there. But you ought to understand, when now you're talking about some of the hardest questions that could be asked. This is aiming high.
What about super martingales and sub martingales?
Can you be a bit more specific?
It's in the review, but I don't recall going over super or sub.
Well, so for a martingale, you would have mn plus 1 given fn. This, your estimate of the future value is just going to be its current value. So if you want to have a super mn plus 1 given fn, if you put in an inequality here, so if we think that the thing is going to go down, then you're going to get a super martingale. And if you want it to go up, we're going to get a sub. So where does it come up? So as an example, for where the martingale property is broken is if you take a convex function, right, so pick your favorite. Pick your favorite. This could be your k minus x positive part, or it could be your square function. Pick something that has convexity in it. And then you use Jensen. Gives for a martingale. What does it give for a martingale? Well, if I take, so martingale is the top part, but this is my martingale property. So Jensen's inequality gives for a martingale and a convex function. If I take f of the conditional expectation of mn plus 1 given fn, this is equal to f of mn. So what does Jensen inequality say? It says that if I have a convex function and I have an expectation, there's a relationship between that and pulling the expectation inside. Which one is biggest? Second one is biggest. So what does that tell you? So this object is a
Is it either gonna? It's gonna be a sub or super martingale, but
it's a submartingale, right? We expect it to go up from where it is.
wait, why is it called a sub and why is it called a super? I'm not sure I understood.
These are just names. Right? So why these names? Is that what you're asking?
Yeah, just so it can remember it. It still can make sense to me.
Yeah. The explanation for this is something that's coming from harmonic analysis.
Okay, I guess that's too. I thought it was gonna be something more basic, but.
So have you ever seen PDEs? Is that something that you've come across? One of the most famous PDEs is the heat equation. So the heat equation says you take the Laplacian. So you take the Laplacian, so it's a function, you take ux, x is equal to something like ut. I don't know if you've seen the heat equation. This is a harmonic equation because you have equality. There's also something called subharmonic and superharmonic functions. And these satisfy this inequality within less than or equal to. And these two words from PDE theory, superharmonic and subharmonic, they are related to supermartingales and submartingales. And this is something we're going to see towards the end of the class when we get Ito's lemma. Okay, so it comes from harmonic analysis, super and super, because they are linked to harmonic functions and superharmonic functions. So when Dupy named it, this is Dupy, the researcher who did this is Lou Dupy. He was the one who discovered the connection, so he was the one who came up with these things. Kimon is also asking, and the two other conditions, yeah, they're the same. The other two are the same. These ones here, you have to change the martingale property to these two inequalities if you want to get a super and super. So I don't remember who asked the question. So somebody who asked this question.
Can you explain why it's a sub-martingale, please?
Because the expectation of f of mn plus 1 given fn, this is going to be bigger than the current value. Which that's what, if you have that property, this is what a sub-martingale is.
Okay, I see it. Thanks.
this is also something that comes up. And we're not going to be doing that in this course. Okay, so no, I want to stop. I want to stop here.
So the mn can be replaced by f of mn as long as there's some sequence of
Yeah, you just have to have a sequence
random
of
variables.
Yeah, that's it.
Got it. Okay.
Yeah, like you cannot talk about a random variable. One random variable cannot be a martingale. That is not possible. Right. So we're also being a bit sloppy here because when we talk about, so when we say mn, if you go up to infinity, it could also just go up to capital N, is a martingale, we are sloppy. Right, because we really should say that mn, fn, and p is a martingale. Because just to check something like the conditional expectation of mn plus 1 given fn is equal to mn, like you need more than just the random variables also. You need fn and you need p. It's not true, so this is important. It's not true that mn is a p martingale. Then this is the same thing as saying like that mn is a, say, p tilde martingale if p is equivalent to p tilde. Like that's not true. So in other words,
Right. Because one of the conditions for martingale is wasn't there something about like it being integrable? And
it all has to be integrable, yeah. But it's more than that.
Yeah, if it
you don't have to be, so you can lose integrability, that's true, and this is going to be enough for it to fail. But even this property here, to compute the left-hand side, you need the measure p. Like for example, and let me just make sure that, so let's take r to be 0. So then if I compute in a binomial model, in a multi-period binomial model, if I am to compute the conditional expectation of Sn plus 1 given Fn, how would I go about doing this? In a multi-period binomial model, I should also, the name of the game is to compute when you want to, chances are that next week you're going to be computing expectations of this form. In one form or shape or another, this is something that you would have to compute. And the way to attack it is to rewrite this random variable in here in terms of something which is Fn measurable and something that is independent. In this particular case, we're in a multi-period binomial model. So it comes from the definition of the stock price at time n plus 1. It is given by the previous stock price times this coin flip variable. And then it becomes a bit easier because this is measurable, so you can travel outside. And this one here is independent, so the conditional expectation of something that is independent is just the expectation. So here I'm left with Sn times the expectation of the coin flip. And I can work out what this is. This is Sn, and then I'll get my P times U plus 1 minus P times D. And if I compute, the same thing, but under the tilde measure, I'll have my Sn plus 1 given Fn. And I'll do exactly the same calculation. I'll get Sn P tilde U plus 1 minus P tilde times D. Right? And what should this here be?
P over 1 plus R.
So R is equal to
bar 0, but it's the same. So it's the same as, because if you're like, you're not, it's going to be 1 plus 0 on the denominator.
Okay, so what is going to be on the right hand side?
SN PU plus 1 minus PD.
Yeah, what does this add up to under the, what does this add up to?
Isn't that 0?
Yeah, not 0, right? 1.
I mean 1. I'm sorry, 1 because it's a risk-free probability measure, I think.
That's right.
Yeah, sorry.
Nope, that's good. That's good. So now you have it. Right. It is not true that you have equivalence between being a p martingale and being a p tilde martingale. Right? Here you have a p tilde martingale. Here, this is not a p martingale. So this shows you that just because you have a martingale structure on the one measure, you may or may not have it on an equivalent measure.
Wait, can you repeat the last statement to complete the proof?
Right, so under p tilde, this object is a martingale, but under p, it may or may not be. So what could it be? So what determines it? Well, it's going to be this quantity here. So if pu plus 1 minus p times d is bigger than 1, what do I get?
It wouldn't be, right?
Yeah.
It's super or sub martingale. I can't remember someone else.
So if it's bigger than 1, this quantity here is going to be strictly bigger than Sn.
So sub.
So it's a sub. And if pu 1 minus p times d is less than 1, it's going to be a super. And of course, if it's equal to 1, it's going to be martingale. Timon is asking if you can talk a little bit about absolute continuity and equivalence. Yes, we can do that. Right, so let me sit down. So we have two probability measures. So we're going to let P and Q be probabilities on F. Right, so remember what that means. F is a sigma algebra. Right, so this is a structure of sets. It's a collection of sets. It's a set of sets that satisfy a bunch of properties. Right, these here are probabilities, so they go from P and Q, they go from F into 0, 1. And they have two properties. They have the property that if I want to measure omega, I'm going to get a 1. If I want to measure a disjoint union, say of events, this is the same thing as summing. This is when these guys are disjoint. Okay, so I have two measures, P and Q, they defined on the same sigma algebra. So now what we're going to be doing is we say that Q is absolutely continuous with respect to P. This is absolutely continuous with respect to P. If P of A is 0, if this implies that Q of A is 0 as well. Okay, so you take a set, you assume that the measure P assigns zero probability to that set. If that implies that Q on that set is 0 as well, we're going to say that Q is absolutely continuous with respect to P. Likewise, P is absolutely continuous with respect to Q if, switch the roles, if Q on the set A being 0, if that implies that P on the set A is 0. And then finally we say that P is equivalent to Q. So this is a P and Q are equivalent if P is absolutely continuous with respect to Q and Q is absolutely continuous with respect to P. Does that make sense? So we could look at some examples. So when Q is absolutely continuous with respect to P, there exists this Radon-Nikodym derivative, dq dp, which is going to be F measurable. So such that a bunch of properties, all one is going to be F measurable. Right, this is where that's where my two probabilities are defined. They're defined on F. So the Radon-Nikodym derivative is going to be F measurable. It's positive. It's not negative. It has expectation. What is the expectation? It's equal to 1. Very good. And the fourth property is that if I want to compute probability Q on a set A, I can do that simply by integrating with respect to P. So I should say here that maybe I should write this out as a theorem instead of saying when. I should say this is a theorem. There should be a theorem here that says that Q is absolutely continuous with respect to P, even only if there exists this Radon-Nikodym derivative. Okay, so this here is Radon-Nikodym's theorem. So Timon, you were the one that asked. Are we good on this? Maybe we can do an example. So we have seen some examples in class, but maybe we can do another one. The one that comes up in Black-Scholes is the following. So this is like a Black-Scholes. This is a Black-Scholes example. So say that I'm looking at random variables. Let me call them delta Bn. Delta Bn, I'm going to look at a bunch of them. I'll look at them from n equals 1 to say infinity. The IID what? Standard normals. Right, so I take a sequence of random variables. I denote those random variables by delta Bn. And then what I do is I define, then I'm going to define B0. I'm going to define B0 to be 0. And I'm going to define Bn plus 1. This is going to be the previous one plus delta Bn plus 1. This is going to be my, this is like a discrete time Brownian motion. So that's something that we will see. That's going to be the first thing that you will see after your oral exams are done, is to talk about Brownian motions. So this is like a discrete time Brownian motion. So I'm going to get, what will I get? I'll get, so Bn is equal to delta B1 plus delta B2 all the way up to delta Bn. Right, so this is going to be standard normal, mean 0, variance, the all independent, right? So the variances is going to be adding up the individual variances. This has variance 1, and so on. This is going to be normally distributed mean 0 and variance n. We could then look at a Radon-Nikodym derivative. So we could define, we could look at a martingale. Right, this is normally distributed, so this cannot be a Radon-Nikodym derivative. But I could define Cn to be the exponential of Bn. If this is to be my Radon-Nikodym derivative, I would need this thing to, well, now it's positive, and I would need it to have expectation 1. So I need to subtract away, what is the expectation of Bn? This is just a little, I do the moment generating function. So E of Bn, what is that equal to?
Do we turn it into an integral?
Yeah, but I was hoping at this point we could be fast.
So it would be like, do you put a dummy variable, e to the dummy variable times the PDF?
Yeah, but we've done that a few times. So if this would be standard normal, would I know how to do it?
Yes, it would just be like e to the 1/2 t squared, something similar like that.
Okay, so that's if it was standard normal. So it's not. How do I make Bn standard normal? The variance is messed up, so I should do something to Bn here.
Can you split it?
Yes, I can split it.
Because it's the summation.
Yes, I can do that. Okay. I was hoping we could just do something like a Bn divided by, what could it be to make it standard normal?
Timon said square root n.
Yeah, so we also need square root n here. So now this would just be, this would be my t. So I'll get that this is equal to e to the 1/2 times square root n squared. So that would be an n. Right? This term here, this one here is standard normal. square root n, I need to square it to get the moment generating function, so I get the n here. So if I want this to have expectation 1, I need
Wait, don't we have the e to the square root? Like one of them is standard normal, and then what about the thing that's getting multiplied by like the square root n on the?
But if I do e to the t x, if x is standard normal, what is this? You just told me, right? It was e.
Yeah, it's this. Yeah, I was trying to figure out if it was a trick question or. All right.
No.
Yeah.
So I promise you, and this is the same thing with the oral exams. There will be no trick questions. Right? I had one student today. He was the guy that was done in 10 minutes. I asked him, so after we were done with the exam, I gave him a question and I said, so you can think about this until the end of the course. If you can answer the question by the end of the course, I'll be really proud. So there'll be no trick questions unless it is explicitly stated that the exam is over. Here's a question for you to think about for a long time. There are no trick questions here. I am not a fan of trick questions at all, in particular in exam situations. There are no trick questions. If you think that the question is so easy, I guarantee you it is because I intended it to be like that. No trick questions. We're not here to play games. Okay? So what you need to do is to take the t and square it. So now look at the right-hand side. Bn over square root of n. Now you have your square root n outside here. But you need to square it. So you're going to get your n.
Oh, I got you. You're taking the bn over n square root n as an x. Okay. Yeah.
Standard normal, right? What's inside the circle is what is standard normal.
Got it. Yeah, I got confused because yeah.
Yes, okay. So now you need to correct with this one. So it has to have minus a half in here. Right, so that's an example of a radical derivative. Right? So you can define now. So for example, so on say on fn, you can define q of a set A simply by calculating the expectation of 1a and then your z n. Right, this here is for A in fn. And of course, you're going to have a consistency property. The consistency property, for example, you could, if you wanted, you could put in, like, since this has to do with n, you could ask what happens if I look at like q n plus 1 evaluated at a. So now I'm going to take a in fn. Right, so this is going to be inside fn plus 1. So if I am to compute what is the probability on one of these later meshes, so this here is by definition the expectation of 1a zn plus 1. Right, that's the definition of qn plus 1. But now I'm working under this assumption that I have a set that lives inside the smaller one. If that's the case, then I can use iterated expectations. So I can take the expectation of a conditional expectation. And what could I, for example, condition on? What could I condition on here?
F of n.
Yeah. Okay, so now 1a was given to be fn measurable, so he can go outside. What about zn plus 1? How do these relate to each other? Like maybe I can
independent.
Let me just write out what cn is. So this is e, and then I'll have bn plus 1 minus 1/2 n plus 1 given fn. There was a question from Raksha. What is 1A? I mean, 1A is 1A. This is our indicator. 1A of omega. This is defined to be 1 if omega is an A and it's 0 else. Actually, it's the indicator.
Professor, did you finish writing?
No, we're not done. I just saw the question out there. So I wanted to stop because if you don't know what 1A is, it's hard to appreciate.
No, the above paper, you didn't finish writing what ZN was after doing the MGF, I think. Oh, never mind. Thanks.
Yeah, I got this term up there. Yeah, so I'm just using this last line I have here. I'm just using this formula. And so now, as was being proposed, we should somehow use independence. So I'm going to create a little bit more space by moving out to the left here. So I have 1A, and let me break this thing up here into, so now we're back to this usual trick. I need to compute this conditional expectation. How should I do it? Well, the way to get started on the thing is writing whatever you have in here in terms of something which is Fn measurable and in terms of something that is independent. Right? Bn plus 1 is not Fn measurable. Bn plus 1 is not independent of Fn. So here comes the hard work. Right? This is where creativity comes in. You need to figure out how to express Bn plus 1 in terms of something that is measurable and something that is independent. So how would we go about doing that? Well, presumably,
is it equal to Bm plus delta Bm plus 1?
Yes. Minus this constant over here. So if that's the case, now we can collect terms here because you're going to have e to the bn minus 1/2 n. So you know what that's equal to. That was equal to Zn. And then there's a correction term, e to the delta bn plus 1 minus 1/2. And so now we're in much better shape because I need to write something that is measurable and something that is independent. Right? And Zn is going to be measurable with respect to Fn. Like we make the, maybe we didn't write that explicitly up here, but we want to have an Fn somewhere, right? We're going to have, let me get a pen. Right, my Fn, this is going to be the sigma algebra that is generated by B0, B1 up to Bn. So here I have measurability and here I have independence. So I can pull out what's known. So that Zn is inside the inner conditional expectation. He can travel outside here. So I'll get Zn out here. And then I'll be left with this term, which is independent. So the conditional expectation of something that is independent is just the unconditional one. So here I'll have E delta Bn plus 1 minus 1/2. Will we good on the last step here? This object here, this is Fn measurable. This quantity here is independent of Fn. Right, so the measurable part, he travels outside the expectation. The independent part, instead of computing the conditional expectation of something that is independent, you just take the unconditional expectation. And what's the expectation of this term we have here? What is the expectation of this one? Richard, now you know it. What is the expectation?
Sorry, I'm not. I
It was this one, right?
Oh, is it the same? Is it? Oh, because it's standard normal. Because bn plus one is they're all standard. Okay.
Yeah. So this here is equal to what?
E to the 1/2 t squared, but we have to.
There's a minus a half here.
We can just break it up into that times negative 1/2, and then move it out on the outside.
Yeah.
The negative 1/2.
What do you get in the end?
So e to the negative 1/2 times e to the 1/2 delta b n plus 1 squared.
No. This is a random variable, right?
Sorry. It's gonna be 1.
Okay.
1 squared.
Okay. So this is equal to 1, right? This is why we did this correction term up here. We needed the CNs to have expectation 1. This is why we did that correction. So this thing here is equal to 1, right? So we get, this is 1 ACN, so this is exactly your QN of A. So we have a consistency problem. So one of you asked early on where you could see more practice problems on something that has to do with the Radon-Nikodym derivative. So this is why I put this example in here. So here's a specific example of something that is pretty advanced when it comes to Radon-Nikodym derivatives and processes. Yeah. And more questions, comments?
Could we talk about there, like, the independence lemma is like an analog of the thing we just did here when we have an independent thing and something that's like fn measurable.
Yes.
But it's for when you have a function.
Yeah. Here we just have a very simple function. It's just the exponential. So that carries over. Like the independence lemma says if I take two random variables, x and y, say that they're independent, and you take a function from R2 to R, I'm going to forget about the integrability properties here. Just try to focus on the gist of it. So then you're interested in computing a conditional expectation of f of x and y given one of the two. But the function we had before was just a product of exponent. Like if f is just an exponential, then an exponential of a sum, then typically you would not have, like before, we would have something like f of x and y. This would just be equal to the exponential of a constant plus another constant. And there you don't really need the independence lemma, because when you're computing the conditional expectation of e to the ax plus by sigma of x, it becomes easier because the exponential of a sum is the product of the individual ones.
Then you can just bring it out because
you just bring it out, right? So then you're done pretty quickly. This just be e to the ax, and then what's left is independent of x, so we just get e of by. But this is not always going to work. But for if you take something that is a little bit more complicated, like if I do sine of x plus y, but now it's a different story. Now it's a different story, right? How do I compute the conditional expectation of sine of x plus y given x? Well, you can still apply the independence lemma, provided that everything is integrable. So let's pretend that that's the case. Well, sine is bounded in absolute value by 1, so we're good there. Okay, so we don't have to worry about integrability. But you can still apply the independence lemma. It says that this thing here is equal to g of x, where g of a is what? Well, what you do is you take the expectation, you replace the measurable quantity by a dummy, here called the dummy for a, and then you take unconditional expectation over the independent component, which is y.
So what does it end up being? If we have, what does g of x actually end up being? Is,
Well, g is this function here. But this is a function of a. What exactly this quantity here is, it depends on y's distribution. Right, so if y has a density, you can write this in terms of an integral. Like say that y has a density, or if it doesn't have a density, you can write it in terms of an integral over its distribution. So sine a plus y, and then it'll be this f of dy. And then if it has a density, you can put the density here, and you can integrate with respect to dy.
So how come we can replace by a dummy variable in this case? Is it because of x?
Because x and y are independent. So the independence lemma says, if I have a function
And
of,
it's measurable.
say again?
And you're saying because we have this, it's conditioned on x, we could replace it?
Yes,
Okay.
that's what the lemma says.
Yes.
Right, this here is going to be equal to g of x. Right, this is not a definition here, right? This is an equality sign. This is a conclusion where g of whatever dummy you want to call it, Rutgers, right? This is now defined as an expectation of f of, take out the measurable part. This is x, so that's my Rutgers. Like I make a deal out of this, calling it Rutgers and calling it a. I'm not calling it x, right? Because capital X is not a dummy. This is a random variable. And when I write functions, that input parameter I have in here by itself doesn't have any meaning. Like capital X has a lot of meaning. Rutgers doesn't have it. It's just a dummy placeholder, whatever you want to call it. Right. So that's your function. That conditional expectation up here can be computed by first computing the function and then replacing the dummy by a random variable, the one you condition. Any more questions on the sheet?
Do you have any time next week where if we don't have our exam next week, we could come and practice some problems?
Yeah, this is going to be impossible. There are too many students. So what we have is this week. We have Thursday night, and then we have Thursday morning, and then we have Friday afternoon.
Okay.
And as I said on the very, very first slide here, if some of you want to try it, you're welcome to. free option. Arbitrage. But otherwise, take advantage of these morning sessions. There are too many students next week. I have the other class and I have your class, and yeah, I can't make all these things work together. So yeah, if you want to come and practice like this one, I would really recommend that you use the office hours on Thursday morning, and then we'll have Thursday night's lecture, and then there'll be another set of office hours on Friday afternoon.
We don't have lectures next week?
No.
Oh, okay.
As I said early on, one of the reasons why these oral exams are typically not done with undergraduates is because it is very time consuming. So we're trying it out here with you guys. We have 25 students that need to go through it. So having lectures on top of it, this is just too much. All right, I think it's time to call it quits for tonight. So please utilize the hours that are coming next week. We have one loose end that we need to tie up next time, so I need to do that. Other than that, next time we're just going to continue having discussions like we had tonight. There's a question for Timon. Yeah, the solutions to homework 5 as well as homework 6, they will be posted. I can post homework 5. You're going to get posted over the weekend because I want the students that need to hand in parts for homework 5 together with homework 6. You're going to need to do that. So I'll post the solutions to homework 5 and 6 over the weekend. All righty. Otherwise, I will see you guys on Thursday.
Thank you, Professor.
You're welcome.